that is benzene. So we'll discuss the generation, the structure, reactivity, and their applications in organic synthesis. Benzene as an important intermediate, and we have to discuss about the chemistry of benzene. We have to first know the structure of benzene, then how is any classification of what benzene, that is types of benzene, how to synthesize it or generation, what are the chemical reactions can be occurred on that benzene, and one more important, that is the applications of what benzene in what the synthesis. Is there any special reactions or anything there that will be discussed under the category of what application? Okay, so what is the benzene now? So benzene is a specific molecule. So it have the two types of what functional groups. First of all, what wine is nothing but a triply bonded system, and benz is related to the aromatic compound. So this type of the compounds are structurally represented as this one. So this is what the benzene molecule, and when I put one extra double bond outside the ring, that type of the molecule or that will generate the triply bonded system or the alkyne kind of molecule. That's why this is called as a benzene. So this type of the molecules are the part of what the alkynes, because it is triply bonded compound, but it is somewhat differ from the alkynes. Now this is the structural representation of benzene molecule. So we'll discuss the introductory part about that benzene, how this cyclohexane, this kind of a molecules are what generated and all these things. Okay, so before that, what are the special characteristic features of that benzene, or we can also call it as what arynes? That arynes are derived from what? Arene. Arene is an aromatic molecule just like a benzene, and here arynes are nothing but the alkynes. Now benzene one can say. So in case of what benzene, it is a neutral. Okay, it is a neutral molecule, and which is formed by neutral compound, no charge on benzene, formed by removal of two ortho substituent from aromatic system. Okay, so this compound is totally neutral, don't have that any charge. So how it is formed now? Suppose I have this is in my benzene molecule, and I am going to just remove the two substituent from that ortho position. Suppose this is an X, this is maybe Y. It may be hydrogen or it may be any heteroatom or etc. By the application of various type of reagent and etc. So if I remove these two X and Y, so I will get this one. Okay, so and that type of the compounds are called as the benzene. So particularly that benzenes are generally obtained by the just removal, okay, of the two ortho substituent, not any other kind of the substituents now. So it is a neutral molecule of the extra double bond. So definitely it is an electron deficient compound. So it is a neutral. It is a neutral having got the extra double bond outside the ring. Okay, it is an electron deficient compound, and the triple bond have the bent geometry. Triple bond have what? Bent geometry. Okay, and it is appeared by removing the just two ortho substituent. So this is one and this is two. So if I remove the two ortho substituents from any benzene or from any arene, it will form a benzene now. And that type of the molecules are called as a arine. We will distinguish these two. Suppose I have a alkene. You know that alkyne. Suppose example alkyne and your molecule is benzene. Both have triple bond, but the difference is what? Structurally, the alkynes are represented as this one, while that benzene are like this one. Okay. Suppose this is a benzene. This is the structure of what alkyne and the benzene. Alkyne is sp hybridized, while benzene is sp2 hybridized. So this molecule is a linear, while this molecule is a bent. This molecule is what? 180 degree of what angle? Here the angle is near about 120. The triply bonded compound, that is alkyne, they are normally behave as a nucleophilic character, but the benzene behave electrophilic character now. And that's why by observing all these factors, so this triple bond is called as a normal triple bond, but this is called as a abnormal triple bond. So why this is so now? Because this is normally, suppose example, this is my hydrogen now. If I remove that hydrogen, it becomes a nucleophilic character. So likewise, the benzene and alkyne are simply called as a normal triple bond and abnormal triple bond. Okay. So this is the basic difference between the alkyne and benzene. So benzenes are formed by the removal of two ortho substituent. Okay. Now you know that the first benzene as an intermediate is suggested by Wittig in 1942. So we'll discuss the history behind what the benzene. Now that benzene are simply the named as 1,2-dihydro. That means at 1,2 position there is a removal of hydrogen side. Example is this one. At 1 and 2 specific position we have only 4 hydrogen. The molecular formula of benzene is C6H4 only. Look at this structure now. Here the 2 hydrogens are already removed from 1,2 position. That's why this molecule is called as a 1,2 dihydro benzene. So this is the name of your compound, that is what the benzene. So from that specific position, that is 1 and 2, we are going to remove that 2 hydrogen, so you will get the benzene. Okay, so this is the simplest form of what the arine, that is what the benzene. And firstly, Wittig suggested the benzene as an intermediate. So Wittig in 1942 suggested benzene as a reactive intermediate. Now similar to that of what benzene, benzenes are nothing but the, here all the atoms in the ring are similar. Example all are carbon. But there are some other examples also be there from which that benzene kind will be developed. Example, look at this one now. This is heterocyclic ring, and I have this kind of the skeleton now. This is pyridine now. From pyridine also I can generate that compound. Okay, and such kind of what molecule in which the triple bond is present on heterocyclic molecule, then such kind of what the rings of such kind of the molecules are called as a heteroines. Heteroines are nothing but the, they are also called as a benzene, but such kind of the molecules don't have what, suppose you look at the first molecule, they don't have what, they don't have what the benzene. Okay, so because it is a non-benzenoid compound, so that means, so these are the also compound in which triple bond is present, and such type of the molecules are called as a heteroines. So what is heteroines now? Again the removal of hydrogen, two hydrogen from some position, that generate the heteroines now, but there is a heteroatoms are there now. So first example is a pyridine. You know that it is derived from pyridine, so that molecule is called as a pyridines. What is the name of this first molecule? This is pyridines. Second molecule is indole now. Basically this molecule is called as a indole, so and that will be called as a indoline. Indo and both molecule have heteroatom. That's why these are called as a heterocyclic arine. We can simply called as a heterocyclic arine. And there are many various types of what heterocyclic arines are there, and they are formed in various reaction also. Example, benzofuran. You know that benzofuran is a type of a hetero aromatic molecule where benzene and this one is given to you now. This molecule is called as a benzofuran. Okay, and suppose I have the bromine at the third position now. This is called what, the bromo or 3 bromo benzofuran on undergo the treatment with the base now. Undergo the what treatment with the base. So what happened with this one now? So by which base will take the proton and undergo the 1-2 elimination. Undergo the what? 1, 2 elimination. So look at this one, and that negative charge is going to be displace the Br now. And finally that will leads to the compound, that is what this. Okay. So this is my this is my what? Benzene. This is my what? The heterocyclic arine from benzofuran now. And suppose any nucleophile is there now. Any nucleophile is there, that will going to be attacked on which carbon now? So there are two carbons are there, this one and this one. You know that the I'm going to react with the carbon where oxygen is there now, because it is more electron deficient. So like this one, and I'm going to react onto that molecule. So this reaction indicate that this is the first reaction that indicate that benzene act as a electrophilic molecule. That means they have electron deficiency. They are participate in the addition reaction. Benzenes are prepared by elimination first. Look at this one. So this hydrogen and bromine is going to be removed from the molecule. So benzenes are prepared by elimination. This reaction is called as a elimination, because this Br and H from adjacent position, they are going to be eliminated. That's why this reaction is called as a elimination reaction. And now further we are going to attack with the any nucleophile external reagent, and that reaction is called as a addition reaction. So benzene reactions are categorized in two ways. One is a it participate in elimination reaction, and then it is called as a addition reaction. So these are the two steps from which we can explain the chemistry behind the benzene. So look at this reaction now. Here suppose we will discuss the benzene only. Suppose I have this is a triple bond now. I can explain this two structure like this fashion. Look at this chemistry behind that benzene now. Benzene is a called abnormal triple bond. It is electrophilic character. If you see the actual charges on that, you will find that so there are positive and negative charges are there. So it is simply act as what the electrophilic molecule. Suppose I have an electrophile, I have a nucleophile. I'm going to react with benzene. So what type of reaction will be there now? So look at this one. I'm going to react on some carbon, one of the carbon of that benzene, and later on this will be my here, and where will be the charge? So this double bond is going to be shift here now. This will be a charge like negative charge, and lastly I'm going to protonate this molecule. Okay, so after the protonation, so I will get the product now like this one. So that indicate that benzene is an electrophilic molecule. We can add any nucleophile easily. That's why these reactions are called as a nucleophilic addition reaction. The next, according to that Wittig, it is the first suggested by that Wittig in 1942. That is what the benzene as and what reactive intermediate. So that compound is simply named as a dihydrobenzene. Okay. Now how this molecule is synthesized now? This molecule is first of all synthesized from halobenzene, and any kind of what halogen we are going to use here now. This is what halobenzene, and I am going to react with very strong base. Example, N-butyl lithium. This is a very powerful and strong base is there now. You know that the main condition is what? If you take the halo compound, there should be orthohydrogen with respect to X. If suppose example this is occupied by methyl and this is also occupied by methyl, then there will be a no reaction. Why? Because base should abstract the proton which is adjacent to the halogen. That's why the main condition is what? Your orthohydrogen is the necessary condition to prepare benzene from halobenzene. So that N-butyl is there, will take the proton will generate the negative charge. Okay, will generate what? The negative charge, like this. So this is example my X, and this is my negative charge. And you know that negative charge have the tendency to easily remove that X, and you will get the benzene. Now this is very simple reaction, but the condition is that you should have the ortho hydrogen. So this type of a reaction is explained by explained in the 1945 after the discovery of what benzene. So in 1945 the first reaction is explained in which benzenes are synthesized, and that's the synthesis given by Gilman. So this is the Gilman experiment. Sorry, this is what Wittig. Okay, because Wittig is the first owner who explained the structure of what the benzene. Wittig benzene in 1942 now. And sometimes this molecule is zwitterionic. This molecule is also called as zwitterion. That means both have charges. Example, if I remove that double bond, and I will also mention that positive and negative. So such type of the molecules is called as zwitterionic molecule because both charges are there now. Okay. Now by using that reaction, we can explain. Suppose I have the methoxy group at this position, and here is the our halogen now. Okay, and I am going to react with sodium and liquid ammonia. What happened with this now? Sodium sodamide NaNH2 in liquid ammonia. So what happened with this sodamide now? Because it is also stronger base like your N-butyl lithium. So this is very powerful base. Will going to search that deficient hydrogen. And again, there is a one more hydrogen which is ortho to X. Where is X now? This one. So this hydrogen is an acidic hydrogen because of what the halogen. We'll take that halogen. We'll take that hydrogen particularly, and remaining groups are what the same. And here I am going to generate the negative charge with the Na plus. Here negative charge with what the lithium plus. So what happened in the next step? That negative charge is going to be displaced, and here the X will be free now. So that means in this reaction, in this what reaction, this is my methoxy group, and here newly formed double bond, and this is called what the substituted benzene is appeared now. Now what happened? What about the charges now? And I have the nucleophile that is NH2 negative ion. So where it going to be attacked now? With respect to OMe group, where it going to be react now? Because there are two carbons are there. This is one and this is two. It is unsymmetric type of what molecule. So that NH2 negative ion is going to a specific position, because in first molecule look this one, your nucleophile is going to be anywhere at on positive. Okay, and I already mentioned that whenever symmetrical type of molecule, we have two structures are appeared now. So this is the first one and this is the second one, but it is unsymmetric. Now NH2 is going to add on, it depend upon that the group which is adjacent to the triple bond. Example this one. So this is O is a, if it is a donor, then your nucleophile cannot be approached with adjacent position. Then that means it causes the repulsion between these two group now. So it should be react at the lower carbon with respect to that OMe, and that's why your resulting product will be expected product will be what? So here this is what OMe, this is what my NH2, and here is the negative charge. Further I will just protonate this molecule and I will get the product. This is what NH2 and this is what OM. Okay, so that means you can prepare the meta substituted product now by using that benzene. Okay, the next reaction, from chlorobenzene we can prepare the aniline now. Aniline cannot be prepared very in simple reaction. We have to do diazotization and all this thing. But in this experiment, we can easily prepare that aniline from what chlorobenzene. Okay, And Robert give the first evidence by using the C14 isotopic labeling experiment. Example: this carbon this carbon is labeled by 14C carbon. Now, what we have to do now? So this compound first of all react with the potassium hydride is a stronger base. Okay, in the presence of ammonia as a solvent. So what happened with this KH now? KH will take the hydrogen which is adjacent to that Cl and generate the negative charge. So what happened with this now? Your carbon is labeled as here. Okay. Next one, this negative charge is going to be react here and Cl is will be free now. So you will get the benzene as an intermediate. This one. So your labeled carbon should be here. Later on, now I am going to add the nucleophile, which is a nucleophile now here, NH2 negative as a nucleophile. Now, in this benzene, both are symmetrical one because it is a simple benzene. So that's why. So there is a chance of NH2 is going to be added here also and NH2 be added here also. So there is a 50-50% chance to react together and there is a formation of the product now. So the product form in equal distribution. Example, this is my NH2 and example, this is also my NH2. Now the labeled CH2, the labeled carbon will be here and here. So you get the equal distribution of the production. But look at the synthesis now. The Cl, so no one nucleophile is going to be add easily here. It is not possible to add the nucleophile on aromatic skeleton. And that's why for aromatic nucleophilic substitution reaction, for what? Aromatic nucleophilic substitution reaction, what we have to going to do now? So we have three types of a reaction, that is ARSN1, that is ARSN2, and that's third important is called as a benzene mechanism. Okay, so in ARSN1 what we have to going to do now? So we are going to use aniline, and on diazotization that will convert into the phenol. What is ARSN2 now? ARSN2 is a type of a reaction where leaving group should be connected, or adjacently there should be electron withdrawing group should be there. Then your incoming nucleophile is there. It's going to easily displace. Just go back, you will find that type of reactions. This is a substitution reaction. And similarly, now we are going to discuss the benzene. So similarly, the benzene chemistry is something is different. So here chlorine is replaced by what? NH2 now. As seen earlier in the reaction in the last slide. So these are the nucleophilic substitution reactions now, which are done on the aromatic skeleton. So benzene is electron rich. Benzene is a electron rich, and I am going to convert benzene into benzene, that is electron deficient, and so I am going to add any. So that means you cannot add any nucleophile onto the benzene now because it is not possible. You cannot remove this chlorine by adding any nucleophile simply. It's very difficult now. You know the Dawes process from chlorobenzene to phenol. It is very drastic. At drastic condition only I can prepare the phenol now. In a drastic condition only I can prepare the phenol from chlorobenzene. But at room temperature, such type of reactions are not feasible. Why? Because of what? Your benzene is an electron-rich molecule, so we cannot add nucleophile. Then how that how that electron density of benzene will going to reduce now? So it only reduces either by inserting more withdrawing groups or by making benzene. If we convert that electron-rich benzene to benzene, then your benzene is electron deficient, and then you can add easily nucleophile, and you will get the required product. So that is the chemistry behind the reaction. Okay, got it? Look at this one now. Yeah, this type of reaction not be possible now because your molecule is already electron rich now. But if I convert that molecule to benzene, so it is possible. Okay, got it? Now what happen when I take such a molecule where no hydrogen which are adjacent to the ortho position of what? Halogen or any living group. Same, I am going to use the sodium sodamide, that is NaNH2, in what? Liquid ammonia. Here that NH2 negative is also act as a base and nucleophile too. So is it possible to this reaction will be going to proceed? So no. So this reaction is cannot be proceed. Why? Because of what? So in this reaction, the benzene is not participated. Why? Because of the hydrogen is not attached to the position. That is to what? Adjacent position. Okay. So whenever leaving group is there, so here X is equal to what? Leaving group now. So adjacent to the leaving group, there should be a hydrogen required now. And that's why if any hydrogen is there, the reaction will be occurred. If no hydrogen, then no reaction will be going to be proceed now. Okay, got it? Now I have one more experiment for you. So what happened when I'm aniline is going to be react? Suppose this is my aniline and I'm going to react with some diazotizing agent, example HNO2 and H2SO4. What happened with this? Yes, so diazotization will be there, and in the next step I'm going to react with water now. So by using all these things, you directly converts into the phenol. This is the mechanism is called ARSN1. This is called ARSN1. And now that ARSN1 will going to again further react with ranitidine now. Ranitidine in presence of a hydrogen at strong condition. So simply it is a reducing agent. It reduces all the double bond which are present in the ring, and you will get this compound. So this is also the reaction. But the first step of this molecule reaction is called as a ARSN1. That is aromatic nucleophilic substitution reaction. Okay. So that makes experiment doesn't prove that in acidic medium that means that NH2 or such kind of the molecule never produces benzene now. So you should require the good living group. You should require that halogen or any other things are there. So to convert that into the benzene. Okay. So then uh, so where that benzene is going to be applied now. Suppose here I am prepared that benzene by specific reaction. Suppose this is my benzene now, and that benzene is going to be react with some molecule. Example, it is a furan. Example, it is a furan. Or you can take simple molecule like this one. Okay, this is a double bond I am going to react here now. And here some withdrawing groups are there attached to that double bond. What type of reaction is this now? So here I am going to use the di now instead of the dienophile. Now the well-known application of that benzene, which is act as a 2 pi electron molecule, and this is going to be attack as a 4 pi molecule now. So 4 plus 2 pi cycloaddition reaction. That means the reaction is going to be form a cyclic product. So this bond will be going to be react here. So this will be going to be here, and this will be going to be here. So this is the 4 plus 2 cycloaddition is going to be takes place, and this is a well-known reaction, and that is called as a Diels-Alder reaction. That means your benzene molecule is participated as a dienophile, and this is going to be called as a diene. So that benzene is easily react with your conjugated molecule, that is diene, and it form a product, and that reaction is called as a Diels-Alder reaction. So that means that your benzene is act as a one reactive partner in the Diels-Alder reaction. So similarly, we have various types of dienes are there. We have cyclic dienes, we have acyclic dienes. Now look the very simple and very common example, this one. Okay, now this is a molecule that is called as a furan, and I am going to react at some specific temperature condition because Diels-Alder reaction is a thermal catalyzed reaction. The reaction is induced by temperature. Okay, that's why it is a thermally induced reaction. Now what happened in this reaction now? Look at this one. Already we have one more cycle. Already we are going to look at this one. So this will be here, and via this carbon it going to react at here. Okay, got it? Now look at this one. This is my a ring which is formed in the which already where the ring is which existed ring, and here I am going to develop a new bond, this one and this one. The remaining things are what same, this one. So where is my furan molecule now? This is my furan now, and here is my double. You get the cyclic intermediate now, right? So in that reaction also, this will be called a dienophile, and this is called as a diene, and you get the cyclic product. Okay. Okay. So next step is what? Is any other method from which benzynes are prepared? Yes, from anthranylic acid. What is that anthranylic acid? You heard about the Gabriel thalamide synthesis or thalamide. You know the thalamide now. This is what CONH. This one. This is called thalamide. Thalamide. Thalamide is undergo the hydrolysis by basic medium reaction. It will be produces amide, and this will be my carboxylic acid. Okay, this is what amide and carboxylic acid. Now that amide is react with your reagent, that is X2 and OH. Which reaction is this? Which reaction is this? Yes. Which reaction is this? कोई रिएक्शन नहीं है. Yes. So this is first hydrolysis. The next one is Hoffman bromamide degradation or Hoffman bromamide rearrangement. Next one is a diazotization. Then third one, this molecule is called anthranylic acid. Anthranylic acid on treatment with the HNO2 and HCl, it will gives that diazonium salt, then undergo the treatment with elimination. So you will get the benzene as a product. So this reaction is also the prepared for, or this reaction is used for making the benzene. Okay. And there are what various reactions are there that will be required to prepare that your desired molecule, that is what the benzene. So I will just list out the some reactants from which we can prepare that benzene. So from this anthranylic acid, that is N2 plus, which is already discussed in the last slide. From this molecule you can prepare benzene. From dihalo compound by the reaction with the magnesium, you can prepare this one. So from simple halobenzene we can prepare your compound, and from cyclic heterocycle like this one we can remove the N2, and this is suppose in my molecule, this is what S double bond O double bond O and this one. So look at this four reaction from which we can prepare the benzene. simple reaction from which we can prepare that molecule. So here the elimination is going to be takes place. If I remove this one like this, and here will be N2 as well as what SO2 is eliminated. Here the base will going to take the proton. Base will going to take the proton. This will be going to be eliminated X now. Benzene is going to prepare. Here we are going to prepare the magnesium now. We are raised the magnesium. So magnesium is going to insert between that one of the X and this one carbon, and then it will be form a organomagnesium, and finally what Mgx2 will be free now. Mgx2, that is a byproduct. And you know that this reaction. So this will be going to shift here, this will be going to be shift here, and this will be free now. So these are the very simple reaction in which what you can prepare the benzene as your desired molecule. Okay, so these are the various reaction, and you know the application of that benzene. So benzene is worked in two important reaction. So suppose this is my benzene. So benzene is well participate in Diels-Alder reaction, or one can call addition reaction. This is what Diels-Alder reaction. We can add a nucleophile onto that. You get the substitute product. Example, this one. Look at this one. Okay, in Diels-Alder reaction, this benzene is worked as a dienophile, while in nucleophilic addition reaction, it can be used as an electrophilic reagent. Now similarly, just like that four reactions, we have again multiple reactions are there. So I'm going to explain you via the flow chart how this benzene is useful, and how one can prepare the benzene from different reactions. So look at the first reaction from halobenzene. Okay, from dihalobenzene, from the different di substrate groups, example X, and this is triflate group is there. From we can prepare using this is tetramethylsilane, and here OTF is there. From this molecule, which is already explained, from that salt of anthranilic acid, from that fluorine and magnesium salt, from that iodine and this is TMS. If you look to this reaction now, you will find that so in various reactions, what benzene is prepared from the removal of two ortho substituent. This is fluorine and what lithium. Now, if you look this reaction, so you will find that so just the removal of one two ortho substituent. So and write down the reagents which are required for the synthesis of what benzene. So and the required reagent for this transformation, first of all, what if either dihalo compound, then you can simply use the magnesium, or you can use the Grignard reagent. Okay, for that X and OTF, you can use the N-butyl lithium. For that TMS and OTF, you can use that Bu4, that is quaternary ammonium salt. For that NnSO2 molecule, you can remove easily at 0 degrees Celsius temperature. Then we have N2 and COO negative. You can just heat it, you get the compound. At 0 degrees Celsius again, you will get this benzene. Then ITMS, you can use that same salt, that is Bu4NF. And for F and lithium, so at low temperature, that is at -25, you will get this one. And you know this reaction with the help of what strong base. So look at this reaction. So from which we can prepare that benzene. Okay, these are the important reactions of what the benzene now. So that is synthesis reaction. Now one more interesting part, that is regioselectivity now in the nucleophilic addition reaction. You know that the benzene is there. Benzene is, so normal benzene means no substitution. Suppose example, this is my benzene. So I am going to add nucleophile at any position because both carbons are same. Okay, and that's why the nucleophile is going to be here also, or the nucleophile is going to be here also. So no any, without any problem or anything. So that nucleophile and that nucleophile, it has a 50-50% probability. You will get this one now. But whenever any, this is what unsubstituted benzene now. So nucleophile is going to be added at any carbon, no problem at all. But the condition is that if whenever a substituent is there now, so then the regions are different now, and that's why we have the regiochemistry of addition reaction onto the what the benzene. And then two types of groups are there, donor as well as water withdrawer. So let's see the example of a withdrawer, and then let's see the example of a donor. So this is my example as a benzene. Here the electron withdrawing group is there now. And one more example, if it is a donor now, and I have the abnormal triple bond is here now. Now where the charges are going to be now, where the positive charge, where the negative charge. You know that electron withdrawing group is withdraw the electron. It withdraw the electrons particularly. So which carbon of that your external double bond is going to be negative, or which is going to be positive. So this type of the chemistry is going to be here now. In withdrawing group, it withdraw the electron. So the electron density from that bond is going to be shifted to electron withdrawer. That's why this carbon should be a negative and this carbon should be a positive because of what the withdrawing nature of that group now. In donor, what happened now? You're in electron donating group. What is going to be happen now? So it donate the electron particularly to the adjacent position. So this bond is going to be shifted like this one. So if you see carefully, you will find that the charges are going to be, this will be the positive and this will be the negative. This will be the positive and this will be the negative. And now based on the charges which are appeared on that molecule, we are going to attack that nucleophile now. And this is my nucleophile. So here in first reaction, nucleophile should be goes to the positive charge. In second nucleophile also. So what happened in the first case? Here, this is my withdrawing group. This is my negative charge and this is my nucleophile. So that withdrawer can easily stabilize that negative charge now because it is adjacent to that position. And in the next category, what happened now? Your donor and electron, your donor and your negative charge are quite separated from each other now. So if you see the chemistry behind the charge and your group, so you can easily understood the mechanism. Donor should be away from the negative charge and withdrawer should be nearer to negative charge. Yes, understood? Simple. If withdrawing group is there, definitely it withdraw the electron now. So adjacent carbon should be the reach now. Then what the lower carbon? So nucleophile will be preferred the lower carbon. The nucleophile will prefer the lower carbon at here now. In the second category, donor is donate the electron. So as per the conjugation rule, so the lower carbon will be reached now. And that's why the nucleophile is going to be attacked at adjacent carbon. So here look at this one. So the relationship between donor and look at the relationship between the donor and this one. Donor and this one. In withdrawer, they are adjacent to each other. They are what? Adjacent to each other. So the negative charge can be stabilized. While the negative charge cannot be nearer to what? Donor. It destabilizes the charge now, and that's why it should be away from the donor. You must remember the regioselectivity or the regiochemistry behind the nucleophilic addition reaction. Okay. Now we'll see the reactions which are going to be takes place on your desired molecule, that is benzene. So if I have this is the benzene, and I'm going to how which type of reactions is going to be proceed now. So first of all, the benzene is participate in the addition reaction, that is disulfide reaction. It is participate in 2+2 reaction also. It is participate in the one 2+2 reaction also. It is participate in simply nucleophilic substitution reaction, nucleophilic addition. Okay, nucleophilic addition. Example, look at this reaction now and find out the reactant, find out the reagent which are used now. This one. So in the first reaction, I am using the furan. Here I am using this molecule. The reaction is going to take place like disulfide fashion. In the second molecule, I am using the 2+2 addition react, 2+2 1. And here NaNH2 in what? Liquid ammonia. And what various reactions are there now? The first reaction is classified as a cycloaddition reaction, that is 4+2. 4+2 cycloaddition. Second reaction is called as a 2+2 cycloaddition. And the third reaction is called as a nucleophilic addition. So this is all about the benzene, which are a very important type of an intermediate and developed by various reactions. And that benzene is what utilized for the nucleophilic attack particularly, because in simple aromatic compounds we cannot add any nucleophile. But if we convert that benzene to benzene, if I have that benzene, I cannot add any NH2 group. Okay, look at the last reaction, that is nucleophilic addition reaction. So that's why first of all I will going to convert that benzene to benzene, and this molecule is nucleophilic one. This is nucleophilic one. I am going to convert into electrophilic one. So I'm just going to decrease the electron density of that molecule now. Okay, and later on the products are formed. Similarly, we have heteroines are also be there now, or heteroarynes. We have heteroarynes are also be there now. And heteroarynes are what? Again, similar reactions to that of, but they are more reactive than simple benzene, because in heteroarynes we have heteroatom, and that heteroatoms in terms of what? Nitrogen, in terms of sulfur, in terms of what? Oxygen. Okay, and heteroarynes are further classified on the basis of ring also. A ring size is 5-member ring, 6-member ring, 5-member, 6-member. So they are also be prepared from the removal of 2 hydrogen. Example, I have suppose this is an heterocyclic molecule, that is 5 or 6. Okay, so this is my molecule, first molecule and second molecule. The first is called as a furan, second is a thiophene, and third is a pyrrole. Now this molecule is participate in the elimination of our 2 hydrogen, which are marked in the red color. If I remove this hydrogen, I am going to prepare the different types of what heteroarynes now. This will be the my double bond which developed here. Okay, so the first molecule is from this is what your furan, this is thiophene, and this is what the pyrrole. Now the first molecule is called dihydrofuran. Dihydrofuran. This is called didihydrothiophene. And the third molecule is called as a didihydropyrrole. Okay, so these are the five member, one can say the heteroarynes. Similarly, we have six member are there. So already we have discussed these two molecules, that is one derived from pyridine and second one derived from indole. This one. So first molecule is called pyridine and this is called as a indole or benzopyrrole, from which we can going to prepare their aryne. This one, and here this one. Okay, and these molecules are called 3,4 didihydropyridine. 3,4, because with respect to nitrogen, these two hydrogens removed from 3 and 4 position. So that's why it is called. Write down the name of this molecule: 3,4 didihydropyridine. 3,4, and this one is a 4,5. 4,5 didihydroindoline now. And there are various reactions of that heteroarynes also. So we are not going to discuss all these things. So up to that, benzynes are very important. Okay, just like benzyne, cyclohexene also be participate in the abnormal triple bond. Now, cyclohexene. Suppose I have this is an cyclohexene now, and how I can prepare that cyclohexane, which is quite difficult again. This one. So how can I prepare this one? And that type of the molecules are called as a cyclohexane. We will take some few reactions of that cyclohexane. Now in cyclohexane, how I can prepare now? But in recent reaction, 2009 and etc. So that molecules are developed now and used in various reactions. Example, suppose I have the chlorine substituted molecule. This is my chlorine and this is my what? That hydrogen. I'm going to use that very strong base, example phenyllithium. So that phenyllithium is going to abstract the hydrogen. Phenyllithium is going to abstract that hydrogen like this one, and here will be the Li. Later on, this negative charge is going to be react, and here the double bond will be developed outside the ring, and that double bond is going to be react with that further PHLi. So it will produces the molecule, that is what is one. Now look at the reaction from which we can prepare the nucleophilic addition product of cyclohexane. So the various reactions are be possible on hexane also, but how to generate that is the more important phenomena. From what the substituted cyclohexene, we can prepare that molecule. So by considering all these factors, we can simply explain that yeah, that arynes are highly reactive intermediate, right? What about this aryne now? Arynes, the arynes are highly reactive, highly reactive intermediate and which undergo the various reactions. Example, polar reaction like substitution reaction, addition reaction, polar reaction, and pericyclic reaction. Okay, I have one double bond and I have conjugated triple bond. Now look at this. Such type of the molecule also produces the benzene. एक क्या है आपका? The first one is a 1,3 diene है. This is 1, this is 2, this is 3, and this is 4. That molecule is called as a 1,3 diene, and this is what simple alkene now. So how this reaction is going to proceed now? It is also the part of cycloaddition reaction. That is what the Diels-Alder reaction. How it is going to be proceed now? But this should be a triple bond. Okay, this is that means this is alkyne, and what we are using the diene now. So how this reaction will be going to proceed now? Look at this. This will be going to react at 1. This will be going to be proceed at this one. This will be going to be react at this fourth end will be going to be react at the this one. Can you make the product of this molecule? Now the in cycloaddition reaction, one thing should be remembered: the number of pi bond broken, that should be equivalent to number of sigma bonds formed in a product. So how many pi bonds are going to be break and how many sigma bonds are going to form now? So you can give the number 2 also. Suppose this is a 5 number and this is 6 number. So first I will make this ring and then I will give the I will give the numbers. This is 5 member ring, this is 6 member ring. This is 1, this is 2, this is 3, and this is 4. Now if we look to the molecule, so at 1 and 2 there is a 1 double bond. 1 and 2 there is a 1 double bond. 2 and 3 there is also double bond. 3 and 4 also are the double bond. 5 and 4 and 6 is the sigma bond. 5 and 1 is a sigma bond, and 5 6 is a this one. And this molecule is nothing but this is a 1 2 3 4 conjugated molecules are there now, very conjugation. So that means one can simply explain or one can simple written this structure in this form. Yes, sir. So what these are the reactions and the chemistry behind what the benzene.